Hello all. In this video we're going to start our exploration of state space search and search as an artificial intelligence technique in itself. In this first video we're going to do an overview and take a look at what we mean by states and state spaces, and then in future videos we'll look at a whole range of different algorithms that can be used to tackle this problem. So we're going to start out looking at my notes document, and I'll remind my students that this notes document is available to you, so you can go and look through and read anything again that might be useful for you. So just to give you a little bit of context, state space search makes certain assumptions about the world, typically, although extensions from the basic state space search algorithms may eliminate some of these assumptions and limitations. But by and large, what we're thinking about with state space search are problems where we're trying to plan ahead and we want an optimal solution. So planning ahead, problem solving, things like solving puzzles, one-player games, or extending into two-player games, finding a path or a route from one place to another. Generally speaking, when we're talking about these, they have certain features in the environment. So the basic algorithms assume that the environment is static. That means the agent is the only thing making changes to the environment. It's fully observable, so we can see everything we need to see. It might be episodic. So we start up in some start state for a problem, we solve the problem, and then we're done. It's not an ongoing, endless process. We typically also assume that the problem space is discrete and that it's deterministic. So there's not a lot of randomness in terms of the effects of the agent's movements. So what does this mean for us in terms of agents? We can have a lot of different agent types, but typically we're looking at model-based agents. So these are agents that have a model of the world within them, perhaps, or some information about the world. Or they might even have goal-based agents, or ones that do utility calculations. But most of these algorithms are focused on just solving a goal that's known to us, that's sort of built into the system. I make a note down here too that's important, which is that oftentimes state space search is a component of a larger AI system. So we may have an AI system that deals with the real world or a complex environment that doesn't have these features, but it may use state space search for a part of what it does. So a robot may have a path planner that is a state space search algorithm, but that's integrated with other components that perform other kinds of behaviors and reasoning. All right, there's some important terminology here that I would like you all to keep in mind as we go forward. We'll use these terms over and over. First of all is that we divide these state space search algorithms into two different categories. There are different terms that get used. I'm going to use these: informed and uninformed. It seems kind of odd to think of an uninformed algorithm, but what we mean is that informed algorithms know more about the problem space, and they are able to estimate how far from the goal they might be, how close they are to solving the problem. They have additional information that lets them do this kind of estimation. An uninformed algorithm doesn't have that. It only knows what it actually uncovers in the process of looking for a solution. It can't predict how far away from a solution it is. So uninformed algorithms are a little less AI-like. Informed algorithms are a little more interesting as an AI tool. Another pair of terms that are also very important to keep in mind are the question of, is it an open loop or a closed loop system? So these two terms get used in robotics, but they also come up in other agent-based discussions. An open loop problem occurs when the planner who's trying to solve the problem assumes that they can generate a perfect solution, and that solution can then be executed perfectly by the agent. So it's an open loop problem because in some sense it's not paying attention to that sense, decide, act loop that we talked about agents having. It's cutting that loop. It's sensing, it's being told a problem, it's making decisions, and it's producing not just a current action, but a whole plan of action. And then it's like, I'm done. I don't need to look at this anymore. You go and carry out these instructions and everything will be fine. That's obviously less realistic in a lot of environments, but it's often an assumption with many of the algorithms we're going to look at. When you do state space search, you typically assume, unless you're doing a particularly fancy extension on one of these algorithms, you typically assume that it's going to just generate a solution and not actually carry it out and verify that it works. A closed loop problem or algorithm or system is one that does have this kind of feedback loop, so that it is executing a plan or a solution as it goes and getting feedback about how it's doing. So for instance, there are algorithms that are used for two-player board games like chess or checkers that are based on the algorithms we're looking at, but two-player games are of necessity closed loop. You can't make a plan for how you're going to win a chess match and play it without any attention paid to what your opponent is doing. You have to make a decision, let your opponent move, see where you are. It has to be this sort of agent-based loop. So you can extend these algorithms to do closed loop work, but much of the time they're thinking of things in an open loop way. All right. Now we have to get into some definitions. We have to pin this down. What is a state? What do we mean by that? What is a state space? And what is state space search? So in my notes here, you'll notice a number of terms that are highlighted in bold. Those are the main terms. These are the things that make a part of a state space system. And so they're the things that you need to be paying the most attention to. All right. I have a phrase here that I want to kind of focus on. So if we have the kind of environment I described a moment ago, then we can think of a particular moment in that environment, a step in that world, as having a configuration. Certain objects are in certain places, certain things are happening, certain information is known, and it's static, so it doesn't change. So if we describe a moment in time, an environment an agent is in at a particular moment in time, that is what we call a state. A state captures all of the relevant information about a moment in this step-by-step environment that our agent is existing in. So we have to be able to define states in a meaningful way to be able to apply state space search to a problem. And it'll turn out that this is a very flexible definition. There are lots of different problems that can be solved using state space search where you can define the problem in terms of states. The easiest to get our fingers on are usually puzzles or pathfinding or things like that, but you can also apply this to really any planning task that you might have. Designing a chemistry experiment, cooking a meal. I could come up with lots of examples, but it's a really, really broad, flexible term, even though it has this very specific set of requirements, right? We need to be able to describe a step, a moment, and what is relevant in the world at that moment. So we have just a state for maybe the current situation, but then we have lots of other states that describe other situations that could possibly occur. So if we look at the set of all possible configurations, any possible configuration the environment could be in at any given time, we call that the state space. It's a space of different states, and they relate to each other, so it's going to turn into a graph ultimately, but we call it a state space. In that state space, there are special states that are important to us. There's the initial state, That just describes the beginning of the current episode. Where are we at the start of our problem solving? That state is special because it's where we begin our search. We start with where we're at and we go from there. Different episodes may have different initial states. They might have different start states. You also have goal states, which represent the solution to the problem. And one of the things that is true of many state spaces is that there could be more than one goal state. Sometimes a goal state only describes part of the configuration of the environment, and so other parts of the environment might vary. And you don't necessarily know. So what we absolutely have to be able to do in order to use state-space search, we have to be able to identify whether or not a state is a goal state, no matter what. We have to be able to tell the difference between goal states and non-goal states. That's not a very high bar, but it's absolutely essential. All right, so we're talked about the state space as being just this collection of configurations. There's also one other piece to our state space, and this is the connections between the states. So the way we think of it is that there are, for the agent, a set of actions that it can take in any given state that affect the state, that change it in some way. Those actions cause us to change from our current state to some other state. And exactly what that other state is, well, that depends on what action you take. So actions turn into the things that connect states to each other. And you could have an action that is reversible. So you're in state A, you take this action and you get to state B. And then there's another action that will take you from B back to A. So just as an example, if you think about a puzzle where you can move a piece and then you're allowed to move it back again, that is a case where you have a reversible situation. Not all problems are reversible. For instance, two-player games, you can't undo moves if you decide to change your mind. So what we do is we imagine that the states in the state space are nodes in a graph, and the actions that connect the states to each other are the edges of the graph. So we basically turn this whole problem into a graph representation of the problem. And the great thing about that is that people have spent many years developing graph search algorithms, and we can apply those algorithms to this problem. In particular, we're going to be looking at breadth-first search, depth-first search, and Dijkstra's algorithm as three examples of algorithms you can apply to this problem. But there are others that you could also find useful. All right, there are some key ideas here that I want to sort of draw out, particularly in the realm of artificial intelligence. We have some state spaces that are quite small. Even complex ones like the state space for playing tic-tac-toe. It's a two-player game. There are a lot of moves, but it's still a relatively small state space. On the other hand, we have state spaces that we can describe that are extremely large and complex. Suppose I have a self-driving car. Theoretically, that car can go anywhere, say in North and South America, if I have it sitting out here on campus. It can go anywhere in North and South America that a car can drive. That's a huge state space. We have to somehow manage really large state spaces sometimes. And sometimes the problem is defined in such a way as that the state space may be effectively infinite. And we can't necessarily use algorithms that assume that we have a complete graph determined. So one of the things we do in AI is we reformulate some of these graph algorithms that you might have seen elsewhere. And instead of assuming we have the whole graph as a data structure, we assume that we start with the initial state and we build just those parts of the graph that seem to be relevant to our problem, only looking at as much of the graph as we need to solve the problem. If I'm trying to get my self-driving car to drive from campus to a location that's a mile away, I don't want to be thinking about driving in Venezuela or driving somewhere in the northern reaches of Canada. That's not relevant. I would like to focus on the part of that state space that is close to where the solution and the problems, where the goal and the initial states are. All right, that just means we have to be really careful that we don't end up accidentally exploring cycles and getting stuck in a loop where we never actually make our way to our solution. Okay, so up to this point, we've talked a lot about terminology and definitions. So hopefully it's given you a little bit of a sense of what states are and what state space search is about. We will look at the next video at some examples of things that can be solved, problems that can be solved with state space search, and we'll kind of focus in on one particular example to help us illustrate the different aspects of the problem. And then we'll jump on into algorithms that solve the state space search problems. I will see you very soon.